The second possible solution is applying ML paradigms, different ML paradigms, which learn from no or limited data. So these are algorithms that can generalize to new or unseen classes or tasks without extensive training data. So even if you do not provide enough data or no data during training time, they will be able to generalize and able to detect new classes or unseen classes during the test time. So these are basically zero shot learning, one shot learning method, few short learning methods. So we'll try to briefly go into each of these. So first is zero shot learning. It tries to model, um, basically tries to in this learning model is trained to recognize classes or tasks it has never seen during training. So it model in this the model is trained to recognize classes or tasks that has not or never seen during training, right? So basically it relies on auxiliary information or class attributes or semantic embeddings and try to naturally learn the language descriptions to bridge this gap between the seen and the unseen classes. So it relies on the auxiliary or proxy information of the class and the class attributes given during training or some kind of information and semantic embeddings and maybe natural language descriptors like how the unseen data looks, all kind of descriptions about that unseen data. Basically it uses all these to bridge the gap between seen and unseen classes, right? So this is pretty much about the zero shot learning where it model is trained to recognize even uh, zero samples are given during the training. Then we have, as the name suggests, one shot learning. As the name suggests, only one labeled example per class is given during training, right? Then the model has to accurately capture the important features or similarities between these examples to perform well on the unseen classes. The model has to capture accurately the important features or similarities between examples to perform well on unseen data. And finally, we have few shot. Again, as the name suggests, we give few samples. So it's an extension to what one shot is. It handle try to learn and handle the differentiating features, allowing the model to generalize for a few samples to recognize on the unseen classes. So generalize on the few samples to be able to distinguish and recognize the unseen classes. Right? So these are some of the methodologies which are available to overcome the challenges during the phase of you know data collection, generation, and preparation. Now let's move on to the next step, which is pre-processing and the challenges involved in here. So basically, pre-processing is important because we may get noisy data during our first step of collection. So we can't again give the noisy data to the model. We have to do something called denoising, or we have to remove the noise as much as possible, because while removing the noise, there may be possibility that we may lose the original data information as well. So the challenges here are excessive noise, deeply integrated within original data. So when it's deeply integrated, it's very hard to remove the noise, that as we may lose some original data information as well. So that is a challenge. Second, we have um, basically when we say noise removal, in some cases the noise added is unknown, and it's very hard to understand what kind of noise is actually affecting the data. So unknown noise information, completely unknown noise information in signals and things like that. So for this we have techniques like noise removal techniques. Basically we have denoising, filtering, smoothing, defogging, deraining, etc. So defogging and deraining basically can be applied in autonomous vehicles data or traffic data, where the data is collected under foggy or rainy or snowy situations. So these are pretty much the methods available for solving the challenges of the pre-processing step. Next, we move on to the annotations and label step. This is again a very important step for the supervised machine learning. And why I particularly am emphasizing these annotations are very important for tasks like detection and segmentation and tracking that we discussed in the previous part. So, why it is a challenging task? Because we have to manually annotate. So, it's a tedious task. It's a tedious task for annotating tasks like detection, segmentation, tracking, etc. So either all the higher end tasks. Why is it's a tedious task? Because In the previous example, as I said, we have to give the bounding box information as a ground truth to the model so that it will learn what is the correct ground truth bounding box for the object detection task. And for the semantic segmentation task, the annotator has to manually sit and each carefully annotate each and every pixel where the object is actually present within the image. If it is one object, it's fine, but if there are more than one object, it usually takes a lot of time to carefully do this labeling and annotation for the segmentation task, and so with the tracking task. And another thing is it needs manual intervention. It needs manual intervention and expertise under you know critical applications like healthcare. Basically, to annotate a segment tumor or segment annotate the segmentation of a tumor, we normal humans cannot do it because we may not identify what exactly a tumor represent. If it's a simple dog or cat or any such images, we can identify that this is a dog, so we can annotate accordingly. But if it's a tumor, only an expert can do that task, and unavailability of experts for doing that task is again a challenge for the annotation step. Now, for doing this, there are for solving these challenges, there are available methods. Basically, it comes from the core of supervised ML, subsets of supervised ML. There is a method called semi-supervised ML, which uses some amount of labeled data and large amount of unlabeled data and try to train a model. So it uses some amount of available training data and large amounts of unlabeled data which we currently have to train a ML model. How it does is basically it trains with whatever amount of data it has, and then during inference it gives the large amounts of unlabeled data to the model, and whatever the model predicts, that can be used as annotations with some error bar, because the model trained on some amount of label data may not be 100% accurate or highly accurate, so we have to go with some amount of noise in the labeling process. Next thing is active learning. So it selects the most informative instances from the label data and trains them using the same process. It selects the most informative instances of the samples from the available labeled data and try to come up with a model, come up with a trained model. Then we have weakly supervised learning. So it's again trains on noisy or partial labels. And finally, we have self-supervised domain adaptation methods. So basically, these are the available different types of methodologies that can be used to solve the challenges of the annotation step.